Can everyone hear me okay? Awesome, let's go. So this is the type session. I think we can all agree types are cool. We like types. They allow us to reason about safety properties of our programs. Awesome. I happen to like compiler optimizations also. I think those are also cool. They make our programs harder, better, faster, stronger. I'd really like to have both of these things together. I would like to have type-safe compiler optimizations. Unfortunately, we don't have that always. And as you may have guessed, what I will be talking about today is that in closure conversion, we don't have both of these. The state of the art for typing closure conversion does not permit common closure optimizations. And that makes me sad. But what if I didn't have to be sad? What if we could type these optimizations? And yeah, that will be this talk. So let's go. What is closure conversion? Well, we have this program, and in this inner scope, we have this local function, and it refers to these local variables x, y, and z. But when we want to lift this to the global scope, we can no longer refer to x, y, and z because they're not in the global scope, they're in this local scope. This doesn't work. Instead, we need to find a way to bring these variables back into scope, and how we're going to do that is we're going to introduce an environment parameter, which will contain the values of these variables that we will project out. Then we're going to package the value of these variables into an environment, which gets packaged together with this function, which will get passed to some end user. So Santa's elves have given us this package. Santa's brought it down the chimney. It's Christmas morning. We want to unwrap it and play with it. What we need is a closure calling convention. So what we want to do, the first thing, is project out the code pointer somehow. Second thing we want to do is project out the environment, and then we're going to want to pass the environment to the code pointer. But what we don't want to do is pass in some value that does not have the right shape, does not have the values of all the variables to the projected code pointer. And this is really the key safety property of closures that we want to verify, that the projected code pointer is called with the packaged environment. Now let's talk about the optimization. The flat closure representation was first introduced about 40 years ago by Cardelli. And the idea is that the closure is represented as this flat structure containing the code pointer and the values of the free variables. And one of the nice things is that the closure is the environment is the closure. So why is that nice? Well, that means that we can simply project out the code pointer and then pass the closure itself as the environment to that projected code pointer. And that means that we only have to do this one projection instead of these two projections. And if this is a recursively called function, that can really add up. So this is the main optimization I want to type, the flat closure representation. We want both of these things. As we're about to find out, the state of the art doesn't support both of them. What is the state of the art? It's the existential closure representation. We're going to give the closure an existentially quantified pair, where the type of the environment is what is being existentially quantified over. So we project out the environment, and it has the existential variable type. And we project out the code pointer, and it's expecting that existentially quantified variable as the type of the environment. But because this is a pair, we see that we're doing these two projections. So this doesn't support the flat closure representation. We have our speed, but we don't have speed, but we do have safety. Now, our approach is the flat closure calculus, or FCC. And we use the flat closure representation, so we have speed, we have the optimization, rather. Fantastic. But how are we going to type check this? So when we form a closure, it has the closure type, but as you may notice, this closure type has no reference to the environment type. So how do we know that when we project out the code pointer, we're going to call it with the correct environment type? In other words, what type do we give to the projected code pointer? Now, again, in the flat closure calling convention, what we want to pass as the environment is the closure itself. So what if we just put the closure into the type? And we can do that using a singleton type. And really, this is the key insight of this paper, that the singleton type perfectly captures the safety property of the flat closure calling convention. Now, of course, because we're using a singleton type, this introduces some dependency into the type system, so we have to add some restrictions to make that work, and we have to add a few lemmas to our type safety proof, namely substitution and some well-formedness. We also have to make sure that the closures are formed properly, but that's an easier problem to solve. So in FCC, we have both the optimization, we support that, and we also have our safety property. But of course, because we don't have a lot of time for these talks, I have been lying, and I will tell you the truth because it makes us look even better. I said we wanted these two properties for safety and the optimization, but there's actually a whole bunch of optimizations for closures who've been pretty well studied. And so we actually come up with 7 requirements for FCC in the paper. And we show that we support all of them, and we can do a bunch of really cool stuff with closure optimizations compared to prior work. So of course, in the paper is all of the meta theory. There is an implementation in Redux of the type system, the language, and optimizations. We also have more optimizations described in the paper, which can be done in a type-directed way, and we give a type-directed formalization of some past optimizations. We also provide a type-preserving translation from the abstract closure calculus. So this is basically a way of showing how you could fit FCC into your existing compiler, even if it's a type-preserving compiler, which is pretty cool. Yeah, if you're interested in more stuff on types and compilers, my co-authors gave a bunch of talks earlier this week, so you can go check those out. And I think I'm going to give you back some extra time to go enjoy break. So thank you.
I'm going to start with a short, maybe cryptic version of this question, and I can expand it as needed. I'm curious if you also considered using row types to get to the same result, and how does that fit into your big table of check marks that you showed us?
Yes, that is a fantastic question. We did, in fact, consider row types, and one of the kind of hidden motivations for this work is that some of my colleagues are interested in doing dependent type preserving compilation, and they have a problem with the existential type because it quantifies over types, which causes issues with impredicativity with dependent types. And we found that the same problem was present when we were trying to do row polymorphism. So that's why we wound up using the singleton type. But we do speculate that for the purpose of the optimizations, it could probably work. Thanks. But we haven't studied it in detail.
Hi, nice work. So I wanted to ask about your closure to result type. I mean, you didn't actually show in the talk what the type would be. And the related thought here is, can't you just use recursive types for that? Because you're passing the closure type. It was closure arrow B.
Let's see. So here, that's it.
Yeah, so that type over there,
yes.
Should we be reading that as closure from A to B to B?
What I mean is that like the box that you extract the code pointer from is what you pass in as the environment. So that's a singleton where the only inhabitant is whatever closure you projected the code pointer out of.
And so then instead of using singleton types, do you think it might make sense to use recursive types?
We do use recursive types.
But that wouldn't give you the guarantee you get with singletons.
Yes, okay. So we do use recursive types for the representation because there's an inherently recursive relationship between the type of the function and the type of the closure because the function is part of the closure. and it also expects the closure as an argument. So we do use a recursive type for that, for representation, but then we have this kind of more abstract notion that uses the singleton type to enforce the calling convention.
Okay, all right, thanks.
All right, we have time for more questions. I guess if there's no question, then we can go to the break. Let's thank the speaker again.